Counting the number of terms in a finite AP. Welcome, everyone. Let's begin our lesson on counting the number of terms in a finite arithmetic progression. Now, in our previous lessons, we focused on a different direction. We learned how to find the value of a specific term if we already knew its position, which we call n. However, in many practical, real-world scenarios, the situation is reversed. Instead of knowing the position, we are often given the starting value and the ending value of a sequence, and our task is to determine exactly how many terms exist in total. This specific process, calculating the total number of terms, which we denote by the letter n within a finite arithmetic progression, is exactly what we are going to master today. Understanding the concept. First, it is important to understand what we mean by a finite AP. Unlike an infinite sequence that goes on forever, a finite arithmetic progression is a sequence that has a definite end. It doesn't just keep going. Because there is an end, we often use a specific notation for that final value. Instead of calling it the nth term, which we've seen written as a subscript n, we often use the letter L to represent the last term. Now, here is the key connection. Even though we call it L, this last term is still technically just the nth term of the sequence. This means we can take the general formula we already know for the nth term, which is a subscript n equals a plus the quantity n minus 1, all multiplied by d, and apply it here. By simply replacing the subscript n with our new symbol, L, our formula becomes L equals a plus the quantity n minus 1 times d. As we move into the next slide, I will show you how we can algebraically rearrange this exact equation to isolate n, which will give us our direct formula for counting the terms. Now that we've established that we are moving from finding specific terms to finding the total count of terms, let's dive into the core concept. Step-by-step process to find n dollar. Now that we understand that the last term, or L, is simply the nth term of our sequence, let's walk through the logical, step-by-step process you should follow to actually calculate the number of terms, n. First, you need to identify the knowns. Before you start any calculations, clearly list out the values you already have. The first term, which we call a, the common difference, and the last term, L. Having these written down prevents simple errors later on. Second, substitute into the formula. Take those values you just identified and plug them into our standard equation. That is, L equals a plus the quantity and minus 1, all multiplied by d. Third, your goal is to isolate the term containing n. To do this, we need to move everything else away from n. Start by subtracting the first term, from both sides of the equation. This leaves you with L minus a equals the quantity and minus 1, multiplied by d. Fourth, we need to divide by the common difference. To get closer to isolating n, divide both sides of the equation by d. Now, the left side becomes the fraction L minus a all over d, and the right side is simply n minus 1. Finally, the fifth step is to solve for n. To get n all by itself, just add 1 to both sides of the equation. This gives us our final handy formula. N equals the fraction L minus a all over d plus 1. Keep this formula in mind, because in the next slide, I'm going to show you how we can apply this exact step-by-step method to solve a real-world problem involving divisibility. Real-world application, divisibility criteria. Now that we have mastered the formula and the step-by-step algebraic process, let's see how this actually works in a practical, real-world scenario. One of the most frequent ways you'll see this concept applied in exams or even in daily life is when you need to count how many numbers within a specific range are divisible by a certain value. Let's look at a concrete example together. Suppose you are asked, how many 3-digit numbers are divisible by 7? To solve this, we need to transform this word problem into an arithmetic progression, just like we discussed in the previous slides. Our first step is to identify the first and last terms of our sequence. Now, be careful here. This is where many students make mistakes. we aren't just looking for the boundaries of three-digit numbers, which are 100 and 999. Instead, we need the first and last numbers that are actually divisible by 7. Let's find the first term, which we call a. The smallest three-digit number is 100. If we divide 100 by 7, we get 14.28. This tells us that 14 is not enough, so the next whole multiple must be 15. If we multiply 7 by 15, we get 105. So our first term, a, is 105. Next, let's find our last term, which we call L. The largest three-digit number is 999. When we divide 999 by 7, we get 142.71. This means the largest multiple of 7 that still fits within our three-digit range is 7 times 142, which equals 994. Therefore, our last term, L, is 994. Finally, step 2 is to identify the common difference. Since we are specifically looking for numbers divisible by 7, our sequence will jump by 7 each time. So, our common difference, D, is simply 7. In the next slide, we will take these identified values and plug them into our formula to find the final answer. Real-world application continued. Now that we have identified our key components, the first term, the last term, and the common difference, let's move on to step 3, where we substitute these values into our formula. We'll use the formula where L equals a plus, n minus 1, times D. Plugging in our specific numbers from the previous slide, we get 994 equals 105 plus n minus 1, all multiplied by 7. Next, we move to step 4, which is the algebraic process of solving for n. Our goal is to isolate n on one side of the equation. First, we'll subtract 105 from both sides. This leaves us with 994 minus 105 equals n minus 1 times 7. When we perform that subtraction, we get 889 equals n minus 1 times 7. To further isolate the term containing n, we now divide both sides of the equation by our common difference, which is 7. This gives us 889 divided by 7 equals n minus 1. Performing that division, we find that 127 equals n minus 1. Finally, to get n all by itself, we simply add 1 to both sides of the equation. So, n equals 127 plus 1, which brings us to our final result, n equals 128. This leads us directly to our conclusion in the next slide, where we can state exactly how many numbers we were looking for. Conclusion of real-world application. So, to wrap up our worked example, we have reached our final conclusion. By applying the formula and solving for n, we have determined that there are exactly 128 three-digit numbers that are divisible by 7. Now, before we move on, I want to pause here and highlight some common pitfalls you might encounter when solving similar problems, so you can ensure your calculations remain accurate. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the formula, it is very easy to make small errors that lead to the wrong answer. Let's look at 3 specific mistakes to watch out for. First, be very careful with the incorrect calculation of your first term, or your last term, L. In the divisibility example we just worked through, many students make the mistake of using the boundaries of the range, like using 100 and 999, instead of finding the actual first and last multiples of 7. Always remember, you must find the specific terms that actually belong to the sequence, not just the start and end of the range. Second, a very frequent error is simply forgetting to add 1. You might perform the calculation of L minus a divided by D and stop right there. It is crucial to remember that the result of that division only tells you the number of gaps or intervals between the terms. To include the very first term in your count, you must add 1 to that value. Finally, keep a close eye on sign errors involving the common difference. If you are working with a decreasing arithmetic progression, your D value will be negative. You must be extremely disciplined in maintaining that negative sign during your division. If you lose track of the sign, you might end up with a negative value for n, and as we will see in our final summary, the number of terms must always be a positive integer. Keep these points in mind as we move to our final key takeaways. Key takeaways. First, remember the core formula we've developed throughout this session. To find the total number of terms, which we call n, in a finite arithmetic progression, you can use the formula. N equals the quantity L minus a all divided by d plus 1. This formula is essentially a shortcut that saves you from having to list out every single number in the sequence. Second, I want to emphasize a very important rule for checking your work. The value of n must always be a positive integer. Since n represents a count of items, you can't have half a term or a negative number of terms. If you finish your calculation and end up with a fraction or a negative value, please stop and recheck your values for the first term, the last term, and the common difference. It's a quick way to catch any arithmetic errors. Finally, keep in mind that this method is incredibly powerful and highly effective for any situation where you need to count elements in a set that follow a linear pattern. As we saw in our example with the multiples of 7, this works perfectly for finding how many numbers in a specific range are divisible by a certain value. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid grasp of this concept. Master these steps, and you'll be able to tackle these counting problems with confidence. Great job today!